Hello, and welcome to Aggressive Physics. Today is day 95. What I'd like to do today is a couple of sample problems dealing with index of refraction, Snell's law, and possibly critical angle. We've been talking about a lot of quantitative representations of light and how to calculate things with new equations, n equals c over v, n1 sine theta 1 equals n2 sine theta 2, the modified version of Snell's law with sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1, and even critical angle where we have theta 2 being 90 degrees. And what I'd like to look at is a few sample problems that might be a little more complex, a little more problem solving involved, and get our brains working a little harder than they have been with our level 1 type problems. So let's look at a couple level 2 type problems now. We'll take out the whiteboard and solve some more complex problems dealing with light and refraction. All right, let's look at a practice problem where we have three materials stacked together. We have air, glycerol, and water. Air is 1, glycerol is 1.47, and water is 1.33. Those are the N values. And the original light ray comes in at 45 degrees. Now, because these are all stacked together, any normal line is going to be the same. So as air goes into glycerol, it's going to turn. But then, because these are all parallel to one another, we have alternate interior angles. So the angle of theta 2 is going to be equal to theta 1 for the next surface. And what we're going to need to do is Snell's law for each surface pair. So n1 is 1, sine 45. n2 is 1.47, sine theta 2. So let's say we get for theta 2. We're ultimately going to have multiple problems to solve in this one practice problem. So sine 45 divided by 1.47, second sine, second answer, we have 28.75 degrees. Now that's the same angle that it's going to hit the glycerol water boundary. So we do it again. n1 sine theta 1 equals n2 sine theta 2. n1, 1.47. Sine 28.75, n2 1.33, sine theta 2. So 1.47 times sine of 28.75 divided by 1.33, second sine, second answer, 32.1 degrees. So that would be here. It gets a little bigger because it bends away. Now, if we had another surface, we would use this answer to do the next problem from there. And as long as we have a stack and they're all parallel, we just use the previous answer as the new angle of incidence for the next part. Now, what we have here is a glass prism like we had before, and actually we're going to make it out of lucite. So that we try a different index of refraction. It's 1.5. And we have light rays coming in, and this is a triangle that's equilateral. So that means each part is 60 degrees. Now, when the light ray hits here, it's going to either bend down or up, depending upon less to more or more to less. Now we have air. So instead of going straight, it's going to get closer to the normal line, so it's going to bend like that. I'm going to draw it dramatically. It probably doesn't bend that much. But let's find theta 2 there. It's going to hit this side, and we're going to have a new problem to deal with. And if I draw the normal line, we have our theta 1 is here. Now, unlike the stack problem, these are not going to be the same. This is not parallel lines that are bisected. So we're going to have to come up with a new method. So let's just solve for this first one first here. n1 sine theta 1, n2 sine theta 2. Air, sine 30, lucite, sine theta 2. So let's solve for theta 2. Sine 30 divided by 1.5. Second sine, second answer. We have 19.5 is theta 2. Now this here is 19.5. That isn't. But if we look at this, this created another triangle, and we know that triangles have 180 degrees. So we need to know angle A, then we need to know angle B, and then we can work our way to get theta 1 for the second combination. Now how are we going to get A? Well, if we look at this surface, remember this dotted line is a normal line. So what we're going to need to do to find A, it's going to be 90 minus 19.5 degrees, and that should get us A. 90 minus answer, getting 70.53. Well, let's just do 70.5 since I rounded it already. 70.5 degrees. And then B is going to be 180 minus 60 minus A, which is 70.5. And that should get us B. So 180 minus 60 minus 70.5 is 180 minus 60 minus 70.5. I hit the wrong button, I guess. In the thousands. 49.5 degrees. Now that's B. But what's theta 1 here for the second boundary? Well, that's the complement as well. So we have to do 90 minus answer, and it's going to be 40.5. Now it's going to hit this boundary. It's going to go back into the air. It wants to go straight, but it's going to bend away from the normal. And this angle theta 2 is going to be bigger than 40. N1 sine theta 1, N2 sine theta 2. We're in the Lucite, so it's 1.5 sine of 40.5 equals 1 sine theta 2. All right, now we just have to mop up. 1.5 times the sine of 40.5, second sine, second answer, and we get 76.95 degrees. So this final angle is going to be 76.95. Pretty big. If this angle were any bigger, like it was in that demo I showed a number of days ago, it would actually hit here and then bounce back. It would be totally internally reflected if we exceeded the critical angle. Now, what was the critical angle, or what is the critical angle for Lucite? Let's figure it out. N1 sine theta 1 equals N2 sine theta 2. We know Lucite's 1.5. We want to find the critical angle. N2 is 1. Sine of 90 is 1. So 1 divided by 1.5, second sine, second answer, and we get 41.8 degrees. We were really close to that critical angle, 41.8 degrees. So if we were slightly bigger, if this was 32 degrees perhaps, we probably would have been trapped inside the prism. So that's the critical angle. Not our answer, but it just showed how close we were to not even escaping into the air in the first place. So a little more complex when it's a triangle, but still doable. You just have to remember some of your geometry facts from earlier in your math classes.